So in the previous video, we used rectangles to estimate the area under the curve. And what we want to do for this next homework assignment is to find the exact area under the curve using rectangles. So we want to, in this first video, just look at the theory behind it, and then subsequent videos will actually do the calculations. So here's an example. So in the previous video, we took a curve. In this case, this is the square root of x that we're looking at. So we took a curve like the square root of x, and we estimated the area underneath the curve by constructing a certain number of rectangles. So the worst possible scenario is we could use a single rectangle like we have here to estimate the area under the curve. So you're going to get an estimated area that has a lot of error. This, in fact, is an overestimate because there's a large portion of the rectangle that's above the curve. So you get an estimated area right here that's significantly larger than the actual area is. And so the key question is to ask yourself, what could you do to improve that area estimate? And the simple answer to that question is just to say, hey, let's take and make more rectangles. Use more rectangles, each of which has a smaller width. So here I've got 3 rectangles, and now you can see that the estimated area went from over 11 to now it's 9, which is much closer to the actual area than that original single rectangle. You still get an overestimate in this particular example. You get these little pieces of rectangle that are above the curve. But of course, we could improve the estimate further simply by taking and constructing more rectangles. So here we're going to shoot for 11 rectangles, and now my estimated area is about 8, and the actual area is about 7.5. And now you can see these error regions where the rectangles are above the curve, giving an overestimate. They are much smaller than they were in the original image. And the idea is we could continue to improve the estimate by making the number of rectangles larger and larger and larger, or the number of rectangles of equal width. So here I have 20 rectangles fit into the curve, and you can see the estimated area is about 7.8 and the actual is about 7.5. So the big idea is that what you really want to do is let the number of rectangles you're using to estimate the area go to infinity. We want to take the limit as the number of rectangles goes to infinity. So here's the big idea. If you want to find the exact area of a region under a curve, so we're going to take a function f of x. So for example, here's a function f of x. As long as it's continuous and non-negative, so we're going to ask for the graph not to go below the x-axis for this particular homework assignment, although we will relax that requirement as we move forward. So we're going to let f of x be continuous and non-negative over some closed interval from a to b. Then we're going to say that the area of the region under that curve, or bounded by the graph and the x-axis, in other words, the area under the curve over the closed interval, is given by, so here we're going to have the summation like we've been doing. We're going to take the sum from I equal 1 to n, where n is the number of rectangles we work with. And then we're going to plug some c sub I on that's associated with each rectangle. C sub I will be an input associated with the ith rectangle. So this is the height of take an estimate for the height of the rectangle times the width of the rectangle to get the area of the rectangle. But what we're going to do now that's different than the previous homework is we're going to let n go to infinity. Delta x will be the same as it was in the previous homework. Delta x is just going to be b minus a. Find the length of the bounded interval divided by n, the number of rectangles you want to work with. And c sub I is going to be any x value in the ith interval or associated with the ith rectangle. So if I just draw a quick picture of what's going on here. Let's say we're wanting to find the area under the curve from A to B. Let's say A and B are located in those 2 locations. And when we construct the rectangles, we can use left endpoints, right endpoints, midpoints. It doesn't matter how we construct the rectangle. So let's suppose that we're using right endpoints. So there's going to be some tick mark. The next tick mark over from the A, we would actually find this by doing A plus. We've got a delta x, so we would want to add 1 delta x, so 1 times delta x. A plus 1 times delta x would get us to the next tick mark. If we were doing right endpoints, we would draw that rectangle up to the curve and then over to the left, and we would drop it down to A, the left bound of the interval. And then we would need a second tick mark. This would be the second number on the x-axis, and this would be A plus. We would be adding the change in x twice. So it would be A plus 2 times delta x, and then we would draw up to the curve from there, and then over to the left and down to the previous bound. And we would keep drawing these in. So we're going to make n rectangles. We're going to make n rectangles, and the idea is we don't want to know up front how many there are, because we're going to take the limit as n goes to infinity. When we get done, the far right endpoint is going to be at B, and from B we'll draw up to the curve and then over to the left and down to the previous tick mark. B will actually be equal to A plus, if there are n rectangles, it's going to be A plus n times delta x. And in fact, you could verify that if you do B equals A plus n times delta x, and recognize that delta x, we've defined delta x here to be b minus a over n, so n times b minus a over n is what delta x is. So you get n divided by n is 1, you get a plus b minus a, and a minus a is 0, you get b. So indeed, b is a plus the nth rectangle times delta x. And then this tick mark right here, this would actually be the tick mark A plus n minus 1 times delta x. N minus 1 is the previous tick mark. And from there we would draw up to the curve, over to the left, and down to the next tick mark, which would be A plus n minus 2 times delta x. Dot, dot, dot. There's going to be n rectangles. We don't know how many there are. At some point there's going to be an ith rectangle. So let's say here is the tick mark associated with the ith rectangle. We'll call that x sub I. And x sub I is just going to equal A plus, it's the ith rectangle, so it's going to be I times delta x. And the tick mark over here associated with making the ith rectangle, which we would draw up to the curve, over to the left and down, this would actually be, we could call this x sub I minus 1, and we would get that by going A plus I minus 1 times the delta x. So this is the ith rectangle. So if we were going to estimate the area of the ith rectangle, so this right here is the ith rectangle area estimate. There's the sub I on the C. The C sub I that's getting plugged into the function is any value on the ith interval. So notice the ith interval goes from x sub I minus 1 to x sub I. C sub I can be any number in that interval. So C sub I will just be any number in the closed interval from x sub I minus 1 up to x sub I. And that includes the endpoints. So C sub I could equal I minus 1, or C sub I could equal x sub I. So we could let C sub I equal those endpoints. So bottom line is to get the exact area under the curve, we break the interval from A to B up into n rectangles. We then take the sum from I equal 1 to the nth rectangle of f of C sub I, where C sub I is any number on the ith interval on the x-axis. We multiply it by delta x, because delta x represents the width of each rectangle. So we're doing an estimated height times width to get the area of the rectangle. And then what we do is take the limit as n goes to infinity. We want to have infinitely many rectangles, because as we get more and more rectangles, the over or under estimates get smaller and smaller and smaller until the rectangles perfectly fit under the curve, giving us the exact area. In the next video, we'll show an example of how to find the exact area under the curve using this definition and limiting process. So we'll use this in the next video to find the area, exact area under a given curve.